Our next speaker is Sastry from JNCASR. He will be talking about stochastic process model in fatigue failure in classes.
Yeah, so it's a great pleasure to be here at this annual event. And in addition to all the other organizers that Samriddhi thanked, I want to thank, where is he? Yeah, I want to thank Samriddhi in particular to accommodate this talk in this program. Okay, so this is work that's sort of part of something that we've been busy with for a while, but I will focus on the most recent part of it, which is being carried out by the Barga Sarkar and Jishnu Nambudri, and several collaborators, Peter Solich and Mohitin Mungan, yeah, that's him, and Jack Parley. Okay, so this work concerns studying the mechanical properties of amorphous solids in particular, and looking at the yielding behavior. And this is something I won't explain, but obviously under the application of sufficient deformation or external stresses, when a material might fail is of importance in a variety of contexts. And so something that we have been busy studying is what happens to glasses that are sheared cyclically back and forth, like this little video shows. And there are several interesting observations that have come out of this line of work using computer simulations. One of which is, if one were to sort of look at what eventual steady states the system reaches and characterize it, let's say, looking at the energy of the glasses per particle, one finds that as a function of the initial energy, which you should read off, going to zero strain amplitude here. If you were to make a sort of a yielding diagram with energy on the y-axis and the strain amplitude, which is the only control parameter that we study, one finds that depending on the initial state of the glass, the yielding behavior is very dramatically different. Well-annealed glasses, which are low energy glasses, show yielding at much larger amplitudes, which may not be surprising, but which are very discontinuous, as opposed to poorly annealed glasses, which have initially high energies, which exhibit annealing, mechanically induced annealing in the pre-yielding phase, followed by yielding behavior that is much more weakly discontinuous. If one looks at the energies of these systems, there's something missing here. Okay. If one looks at the energy, that was not intentional. If one looks at the energy or the displacements from cycle to cycle of particles, there's something interesting, which is what I'll focus on today, which is that even in the cases where eventually the glass will yield at sufficiently large number of cycles, the initial behavior of the system is to anneal. So the energy of the glass will go to lower and lower energies before something triggers failure in the system, and the energy goes up. This is also accompanied by some measure of reorganization in the glasses, also exhibiting non-monotonic behavior. So this is one thing that we would like to have some way of describing and understanding. The second thing that's quite a remarkable character of this yielding transition is that the time it takes to approach the steady states diverges at the equilibrium transition. Okay, so we've been sort of trying to come up with simple-minded ways of trying to understand why these phenomena happen, and what I'm going to tell you is sort of like models that we have looked at, which help us reproduce this behavior and hopefully give us a better understanding. Okay, so in addition to computer simulations from which those data sets came, we've been looking at a couple of different ways of investigating this problem. One of which is to work with simplified single-site and further models of plasticity and mean field calculations, and this is what I want to tell you about. So the basic idea is if you want a model which describes this observed phenomenon of mechanically induced annealing, you must think in terms of your system as having a distribution of energy states. So there's a density of states, and then you further need to have some description of local elasticity, so that if you deform the system by small amounts, you will have some elastic response. But this elastic response will last only up to some finite range of deformation, at which time or at which point your system will become unstable and make a transition to a new glass, right? One is thinking in terms of a local description of what's happening in some region of the glass, and so you have these characterizations of the energy at the minimum, the strain at which that minimum exists, a range, a stability range in terms of strain over which this particular locally stable configuration exists, and then some rule for making transitions from one such minimum, or what we call a mesostate, to another. And with this, one can ask, what does the dynamics of the system give you? And in particular, with some density of states of energy at the minima, if I start at different energies, what is my dynamics? It turns out that you get a yielding diagram which looks rather similar to what one finds in computer simulations, except that comparison turns out to be a little misleading, because this is behavior that you see at some finite time, finite number of cycles. The model, as I described, does not have a genuine transition. And so what I'm going to be telling you subsequently is sort of attempts to get closer to a model and a description that have a genuine transition. Okay, so in order to do that, we've sort of simplified this model even further. So the basic idea is this. So if I take, okay. So basically, if I look at the state of the system going from one cycle to the other, if I'm at sufficiently low energy so that I'm stable, I do not change my state. But if I'm at a high enough energy, which means that a small enough stability range, so that the deformation I'm applying goes beyond that range, I expect a change from one cycle to the other. And I can think of this system in a simplified way. Really sorry, I was watching, but okay. I can think of the system as a random walk with a random walk in a potential with an absorbing boundary. Okay, and this is sort of step one, which captures a lot of the similar behavior that I described, but it also has a time to, well, basically the hitting time, which determines whatever I might see as yielding behavior. But I can go a step further and ask what happens if the stable states that are stable with respect to mechanical deformation have some other mechanism by which they can escape. Okay, so when one introduces this escape time, one begins to see behavior that's closer to a genuine transition. But one can introduce this escape mechanism in two ways. One can think of thermally activated escape, but something that turns out to be much more appropriate and interesting is to think of escape happening through mechanically induced noise due to plastic activity elsewhere in the system, right? And when you introduce that, there is a feedback, because whatever states that are, or if I imagine my system as composed of regions described by my probability distribution, and there are unstable and stable states, the probability of being in an unstable state determines the mechanical noise level. And I'm sorry about running over time, but when you introduce this feedback, one gets a genuine dynamical transition with diverging timescales, except that the exponent turns out to be different from what you see in simulation, and that's something else to deal with. And finally, one can also look at a certain way of ghost-graining dynamics, which successfully captures the non-monotonic behavior that one observes. I will stop here. Here's a quick summary, and I'll be happy to take any questions.
Questions?
Hi. So what are the challenges to reduce the energy of a system continuously only with shear? Because shear can bring it down little bit, but the more annealing is thermal basically, if I understood correctly.
No, so I mean, in terms of what we're trying to do, so the different sort of generations of the model that I described come closer to describing what might really happen in a glass. So the one thing that is, I mean, people know this, we didn't propose it for the first time. The idea is that if I have some plastic rearrangement in one region of space, this is a source of mechanical noise for the rest of the system. So there is that cooperativity, which is important in order to have a yielding transition that's sharply defined.
So let's thank the speaker once again.